Well, hello everyone. I know most of you, but for the few that I don't, I'm Trey Pietras, senior in aerospace engineering at Embry-Riddle Aeronautical University. When I first got to Embry-Riddle, I went out to one of the NAR events, the Bunnell Blast up in Bunnell, Florida, and we launched this rocket, which we call Black Mamba, on I think it was a G motor, and had great success with it. It was we manufactured it ourselves. It was carbon fiber. We used the rocket for the competition every year. It's a hybrid rocket competition where schools like FIU and FIT, Embry-Riddle, UCF, they come out and it's not only a student hybrid competition, but also whoever wants to make their own. Consistently, we're the only ones to make our entire system ourselves. That goes for the umbilical system, the ground system, the control system, and the rocket ourselves. A lot of people will make their own hybrid grains, but then they'll buy a commercial rocket and launch it, or they'll buy certain components stock. But we have this guy here. He's an electrical engineer, and so he actually makes all of the electronics for the thing himself. And we've had variable success with the project, but we've taken a couple of years off of the competition itself to work on what we've got is an experimental hybrid that we've worked on. And so the purpose of this hybrid is to try and gain some data. It's not going to it won't fly, but it's an entirely modular assembly. So you can take things apart. You can add a section to your combustion chamber. You can shape different propellant grains. You can make your chamber volume larger. The purpose with that is to try and figure out what's better as far as geometries, mass flow rates, change up your mass flow rate, change up your flows, and just try and optimize what you can get out of a hybrid engine. And then we'll take that back to the hybrid competition probably either this year or next year, and hopefully have a lot more success with the project. Also worked on another liquid project. This is the test stand that we actually are going to be testing. We haven't found a place to test yet. Normally we test just behind our engineering building, but that's a vertical test assembly, and with this, since it's horizontal and much higher thrust, we might have to find another location to test. Normally we just take it out back and test, but we're starting to make engines too large to do that. Some of these rockets here, when I got to Embry-Riddle, a lot of students were working on their own model rocket assemblies. We got this one here, this one here. The ones we've used in hybrids competitions are the one on the top, this one here, and then our newest one we're actually going to be firing this April. We've test fired it on a G motor, and it flew successfully. The parachute actually didn't deploy, it popped but didn't open up and expand. It just tumbled back down, and there wasn't a scratch on it when it landed, which was phenomenal. So that's how I got really excited with rockets, was working on small stuff like that. There was Aquila is this a liquid fueled rocket that was initially a senior design project under Dr. Eric Perel. The goal was there was a proof of concept to try and be kind of like the first step towards Embry-Riddle's orbital launch initiative, which is to put a satellite into orbit off of an Embry-Riddle made propulsion system by the year 2020. So this project, it's a regeneratively cooled liquid rocket engine. So you have fuel running down through these tubes on the sides, down into the bottom of the combustion chamber, then it flows back up. It serves to cool the combustion chamber, but also to preheat the fuel so that it actually has more energy capacity when you're running it in your engine. The interior of the engine is copper, because of its high heat transfer rate. This rocket is about when I inherited this rocket, it would have been fall of 2011. The school decided they didn't want to pursue. Well, we thought the school was no longer interested in pursuing rocket projects at all, and so we were scraping by. We found funding with Florida Space Grant Consortium, funding from the university. Pratt & Whitney Rocketdyne gave us some money to try and finish this project, and we're at about 90%. But then we are starting to run into the problem of people graduating and people losing interest. And so last year was very productive. We got it to the state that it's in now, but 2 of the guys graduated, and I was the only one left. This is the avionics and pressurant system. The black tank, we repurposed a high-pressure nitrogen COPV paintball tank, and that thing is it's rated to operate consistently at 4,000, but doesn't actually rupture until about 9,000. We're going to be running it at 3,700 psi, and that'll be the pressure system for the engine. We also operate, this is a very low budget project, but we tried to make things as legitimate as possible. We used XB antennas mounted to Arduinos. We actually used Arduinos as our outputs and our inputs. We used them for data acquisition from the pressure sensors on board as well. We got fairly good accuracy off of the Arduino, not something to the level of something like a piezoelectronic where you'd have incredibly high accuracy out of your engines, or high accuracy out of your sensors, but it was definitely good enough for what we wanted to do. As it sits now, about 90% done. All that needs to really be finished on the thing is get a propellant tank machine. We're actually going to be going with a concentric propellant tank design. So the oxidizer tank sits inside of the fuel tank. So you have 2 tanks in one cylindrical assembly, and then they'll both feed straight down into the engine itself. But we need to finish that. We need to finish the umbilical system for that, and then it should be ready to test fire and launch. Still working out where exactly we're going to test fire this thing, but we have some agreements to test low amounts of propellant at a future Volusia County landfill site, not too far from campus. So Icarus was a project that we realized that the school actually did want to continue funding rocket projects, but they wanted to do it on a much larger scale. They said, we don't really care about doing small stuff. Let's just go ahead and try and build a rocket to go really, really high. So this one's going to go to 100 kilometers. Its fuels, it's using cryogenic liquid oxygen for its oxidizer and isopropyl alcohol for the fuel, but we might be changing that to ethanol. Might see as high as a 40 seconds specific impulse increase, which would dramatically increase the efficiency of the engine. Engine itself, or the rocket itself, we predict to be about 17 feet long and about 20 inches in diameter. It uses gaseous helium. We actually calculated about 7 pounds of helium is going to be needed to pressurize this thing. When you're talking about pounds of helium, with how light helium is, you can think about how expensive it's going to be. The rocket should weigh about 760 pounds, and it'll be 460 of that will be the propellant, and then the other 300 will be the structural and the inert mass that you won't get any thrust out of. So 8 of us got together, and we, just off of the specific impulse and thrust and altitude requirements, we came up with an engine design that would meet the needs. The engine itself, diameter of the nozzle is about that big. The throat diameter is about 8 or 9 inches. It's much larger than anything we've worked on before. So we came up with this design, and when we were manufacturing it, one of the troubles with manufacturing we've always found is that no one wants to do one-offs. They're always looking to do a lot of products, like millions on millions of stuff. And so we found a company called Jet Machine Design over in Sanford, Orlando. And at the time, they were really interested in helping us with our research project. At the time, they were actually working on stuff for the Orion capsule. So stuff that there wouldn't be too much of, and they were happy to help us out. We used steel for the first test article. We're using a pintle injector design, so it drops down into the engine, and then the oxidizer shoots out sideways from the pintle, and then fuel shoots straight down, and then you have a shearing effect with the propellants, and they atomize as optimally as possible. So this first design is going to be steel. We predict that we won't be able to test this thing for very long when we do it. We're just going to be trying to take it to steady state for the first few tests. With a liquid, thankfully, you don't have to worry too much about changing. With a hybrid or a solid, you have constant changing surface areas, and you have to worry about the thrust profile for the entire flight. With a liquid, thankfully, all you have to worry about is once you get it to steady state, as long as you can keep those steady state conditions, you only need to test for a couple of seconds once you successfully test fire the engine. Future iterations, we're probably going to use an ablative. The problem with steel is it's really heavy, and so we'll probably have a thin layer, either aluminum or steel, on the outside of the nozzle, and then the inside will be an ablative or ceramic, possibly graphite, to help with heat absorption and also to save on weight cost as well. This will the pintle itself will probably wind up being made of titanium, which, and because it's going to be burning for upwards of 30 to 35 seconds in flight, it'll see a lot of thermal stress, and titanium is just about the only thing we could find that wasn't on the level of mass to have like something like ostium, to where it would be really, really heavy. The propellant tanks were, I'm not exactly sure where they were manufactured, but they were repurposed from an old Embry-Riddle rocket project that metaphorically and literally didn't get off the ground at all. It just kind of, that was part of the tail end of the old AIAA projects transitioning into this project, and we had these tanks lying around in the old in one of the rocket labs, and we just kind of took them and said these are ours now. As far as testing, we use National Instruments LabVIEW and data acquisition units that are built by National Instruments as well. They work really well together. These DACs and analog output devices are triggering the ball valves and throttle valve assembly that we've set up. The way they work is they have a solenoid inside. When you trigger the solenoid, they have bleed pneumatic air that runs and will actually open the valve. It operates at about 100 psi. You feed 100 psi to the valve, and it'll snap open when you open the solenoid. The throttle valves are entirely current driven, so you feed them 24 volts and then also a varying current source between 0 and 20 milliamps, and it'll, based on the amount of current you give to it, it'll open a percentage of that, open a percentage of the total open of 90 degrees based on how much you feed to it. So when we assemble everything, we hook it up to the nitrogen, and about a mile of Teflon tape later, we get we're ready to test. We had one of our first cryo tests a couple weeks ago, and it was successful. We had a couple leaks, but nothing too bad. There was nothing. We did the cryo test with liquid nitrogen because it's inert and it's also much colder. So since it's colder than liquid oxygen is, we know that if we're good with liquid nitrogen, we're definitely going to be good with liquid oxygen. Thinking back to when we did the test, we probably should have pulled it all the way out of the garage, because we actually filled that volume of the garage rather quickly with the. It was all gaseous by the time it was coming out of the engine, but we filled the entire volume of the garage with just that cloud. We did have the garage door open, and everyone except for the guy who was going to check the leak right there was standing outside so that they didn't get oxygen deprivation from being inside there. But it was cold in there for sure. That guy has a coat on and welding gloves and a face shield. That's the aftermath of what the engine looked like afterwards. Someone actually wrote cold onto the nozzle with their hand. So we had a lot of condensation freeze on the engine itself. It resulted in there actually being some rust on the engine, but it was just surface rust that we were able to work off. There was rust on the pintle inside the engine, which had me really nervous, but we were actually able to get that off very easily as well. Plans for the project, we're really close to test fire if we can stop having bad luck. We blew up one of our power sources accidentally a few weeks ago. We got that replaced rather quickly. We are having some trouble with our AN fittings because repeated taking them on and off, we've kind of destroyed the threads on the fittings. So when we were going to order new fittings, and then we're going to have to bend and flare new pipe, and then once everything doesn't leak, we're going to cryo test it, and then we'll take it up to Jacksonville to test. We could, if we got everything to stop leaking, we could probably have a turnaround of about a week as far as the test fire goes. Once the test fire happens, we will take the data, the thrust data, the pressure data that we see, and kind of figure out where we're at as far as, is this a good chamber, the chamber geometry that we were thinking, are we getting the ISPs that we were predicting, is it higher, is it lower? We think if we get our mass flows correct, that we might actually see a higher ISP than we were targeting for the project, which is definitely a good thing. Once we have that design finished, we will go into flight vehicle design. We'll start working on manufacturing the engine that's going to have a graphite lining on the inside. It's really difficult to find people who will manufacture graphite because it's really, really toxic to work with in machining. People who work in machining with graphite often wind up with cancer in about 20 years. But thankfully technology has gotten better, and we have had graphite nozzles machined in the past by a guy local to Daytona. Not sure if he'll be able, those were small graphite nozzles though, not sure if he'll be able to go full scale with it, but we'll have to see. If everything goes well, hopefully we'll be launching next summer. So the way that ERPL's kind of going, all rocketry, especially propulsion side with Embry-Riddle, when I got there were a lot of people making their rocket kits and getting their certifications through NAR or through AAA. It kind of died off, at least on the side that I saw. And so what we're doing with ERPL, Experimental Rocket Propulsion Labs, which I'm president of, is we're actually sponsoring students to get their level 1 certifications. So they pay $20 to be a member of the organization, and then they certify with NAR, and then we buy the model rocket for them, we buy the motor for them, buy all the epoxy for them, and they can get their level 1 certification, no strings attached at all. And we bought 20 model kits, and 20 people raised their, I think 25 people raised their hands, and it was like, well, we have 20 model kits, but if you don't get one this year, we'll have one for you next year. I feel like since I'm graduating, I got to try and keep people excited about rockets, and hopefully I won't be around for when we're actually meeting the Orbital Launch Initiative, but maybe someone who's building one of these model rockets here is going to be the one in charge of that project. Questions?
Well, based on what I was hearing you saying, that you are working with a local rocket club, an R or a AAA club, because even like that G motor, you said that was a homemade?
Oh, it was. I think Cicerone made that motor. Actually.
Oh, it was a Cicerone. I thought you were saying that was a hybrid G.
The hybrids we make ourselves, but the solid that we were wanting to test the airframe of the rocket itself just to see how it flew, make sure we have everything balanced right, and so we took a G motor Cicerone out to Banal Blast and made sure the rocket worked, and then we made our own hybrid motor for the competition that's held every April. Okay,
because there are certain federal regulations and FAR regulations that govern the launching of those kind of motors and rockets, and hope that you're staying in compliance.
We are. We're always doing them at NAR sponsored events.
Yeah. NAR doesn't usually allow EX motors.
EX?
The hybrid. If you made that motor, that's an EX. I don't believe that NAR allows any EX motor launches. Only AAA does.
No, the ones we use in nitrous.
It's HTPB and nitrous.
It's an EX if it's a commercially purchased motor. If you made your own fuel grain, that's an EX motor. NAR doesn't allow EX motors.
Maybe it's a AAA. I know that NAR and AAA both sponsor the Banal Blast event. And,
okay. Well, then I forgot AAA. That's why I'm in both organizations. And
okay.
With groups like you, I generally encourage you to go more towards AAA because you're generally doing more of the EX. And NAR tends to be more conservative and not so much, but the NAR prices and support tends to be a little bit better than the AAA. So.
Right. Yeah. What I found with NAR was that for students, especially for for funding people to get their own rocket certifications, NAR is better.
Yes.
But if you're over the age of 21, it's more expensive than AAA is. So
yes.
We've kind of, for people, we don't have many members who are over 21 who are looking to do this. A lot of them had either already got their certifications or weren't really that interested at this point. They're working on bigger rockets. I've never gotten a certification myself. I just work on big liquid engines. So the couple people who would have had to pay $60 as opposed to $20, we helped them out and say, if you pay the $60, you won't have to pay dues to the club. Just things to try and help them out. AAA is really great for experimental stuff. We knew that we would never be able to test the liquid Aquila. Let's go all the way back. We knew we'd never be able to test this at a NAR sponsored event, but we could take it over to AAA in Tampa and potentially get a waiver filled out so where we could actually test this liquid engine over there.
Yeah, I don't know what kind of waivers they're getting down here. Yeah, I could do 18,000 up there.
18,000. Yeah. Yeah, it's not a question of stealing with this engine. It won't go higher than 10,000 feet, and that's the ceiling up at Vanel. But the trouble is that particular launch program that they have up there doesn't really allow for much experimental at all.
Yeah.
Any other questions?
What's the total loaded weight?
The total loaded weight on this one? On this guy, it was not the most efficiently. The guys who first came up with the design for this rocket and were already halfway through making it, it's not as what you would think of as a conventional large launch rocket to where your structural coefficient is like 10%. I think we only have like 15 pounds of propellant on this thing, and it might weigh 60 pounds. So it's not really that great as far as an efficiency coefficient goes. But I think, yeah, they predicted it to weigh about 100 pounds. We were able to shave off about 40 pounds on that, though. The guys, again, they kind of knew what they were doing, but there was, I mean, the trouble with that I've found without, the only reason I've been able to successfully work on so much of this hands-on stuff at Embry-Riddle is because I've chased grant proposals for my entire 4 years here. And a lot of people, you know, they sit in the theoretical and they're in the classroom, they're designing all their rockets, and then they go to build something and you have, you know, a valve that doesn't come any smaller than a certain size, and then the motor to turn it is too big to fit inside the assembly of the rocket. So there are things they didn't consider. The ball valves actually sit incredibly tight. It's a 6-inch diameter on this rocket, and the ball valves sit incredibly tight. We had to take the cases off of the ball valves and make out of composites our own cases that were smaller and thinner so that we could actually fit them inside. Anything else?
Another thing to watch out with your liquid fueled rockets is they tend to be very tail heavy, which can definitely bring your center of gravity farther out. And then when you expend your fuel, depending on which tank you put where, you can definitely end up with a very radical shift of CG during early thrust.
Yeah, our plan with the concentric tank design was to put the concentric tank right at the center of mass, so that as you depleted your fuel, you didn't see too drastic a change in your CG with the rocket. And then you put weights in the nose cone of the rocket to help balance it better, and hopefully we won't see anything terrible happen during flight. I'm pretty confident it won't happen.
A lot of times you put some, your avionics package as far forward as you can.
Put it all the way up in the nose.
Or something, put some mass forward.
There are some of the airplanes at Embry-Riddle, when they changed out the engines on them, they were actually about 100 pounds. The engines were about 100 pounds lighter, and it threw off the CG on the airplane so bad they actually have 60 pounds of lead in the nose cones of all the diamonds at Embry-Riddle. Yeah, it's just lead blocks that they dumped into the front of the
sandbags. Yeah, sandbags.
Anything else?